problems, what we're talking about is something with respect to time. That is the key here. You're used to looking at problems up till this point, and if I say, here's your equation, 2x plus 1, and I say, if x is equal to 2, then y is equal to 2 times 2 plus 1, so we get 5, all right? It's a static problem, all right? When x is a certain number, y is a certain number. When we first started looking at limits, we talked about what is happening as the function gets closer to a number, okay? And the same as rates. We're asking how fast is something changing at a certain point in time? And if we're talking about how fast something is changing with respect to time, we're talking about derivatives, okay? So just as a practice question, if we have volume of water in a conical tank, that just means a cone. When I say conical, I will give you all the formulas for shapes. All right, so we have a cone. Formula for volume of a cone is pi over 3 r squared h. I would give you that formula in an assignment or a test. So these are all implicit differentiation problems, okay? Because we're deriving with respect to time. So if I want to know how fast the volume is changing, all right? The draining of water, so it's how fast the volume is changing. I derive this equation with respect to time. So what's the derivative of v with respect to time? We would say v prime, but we're going to say dv dt, the change in volume with respect to time. That is v prime, essentially. But the reason I'm going to write it this way, dv dt, is because we need to know that everything is with respect to time. And instead of writing v primed, it makes a little more sense when you're talking about these type of problems. So derivative of volume with respect to time is dv dt. Pi over 3 is a constant, so I can just pull that out, leave it there. What rule do I need to use on r squared h? Product rule, okay? Which says the derivative of the first one. What's the derivative of r squared with respect to time? 2r r prime, but we're not going to write r prime. We're going to write dr dt, okay? So 2r times dr dt times h plus, what's the derivative of h with respect to time? H primed or dh dt times the first one, which is r squared. So that is essentially the same as this. Look, if you write r primed, h primed, I won't mark it wrong, but just be aware that if you go to university, because it's not technically, profs probably wouldn't like it. All right, the Math 100 teacher would not like that. He would want you to write dr dt, dh dt. Yeah. So this, you could write this, pi over 3, 2r, r primed times h plus h prime times r squared. The problem with the primes is you can get confused with them being ones too, okay? I would prefer this, university would prefer that, but if you write this, I won't mark it wrong, okay? All right, so that's just this is now a formula that represents how fast the volume is changing with respect to time. We need to know how fast the radius is changing and how fast the height is changing. But if I give you those pieces of information, you can calculate how fast the water is draining out. All right. Let's go to the question number 3 at the bottom here. This will be the beginning problems that you will see. So we drop a pebble into a pond, causes ripples to move out. We've all seen this happen. The radius of the outer is increasing at a constant rate of 1 foot per second. Then it says, when the radius is 4 feet, what is the rate? At what rate is the total area of the disturbed water changing? Okay. What shape do we have here? You have a circle. I'm asking for area of a circle. What's area of a circle? Pi r squared. So there's our base formula. I need to know how fast the area is changing with respect to time. So what do I do? It's the only thing you know how to do. Derive it. If you don't know what to do, we're in derivatives. We haven't got to integration yet. Derive it. So derive it with respect to time. So what's the derivative of A with respect to time? dA over dt, or A primed. Pi is a constant, so you can pull that out. What's the derivative of R with R squared with respect to time? There you go. Okay, so there's our formula. I need to know R and dr dt. I know R. I think, yep, they tell us when the radius is 4. So there's your R. What's dr dt? Sorry? Yep, but it has a number in this case. This bit right here, 1 foot per second. The radius of the outer ripple. So this is dr dt is 1 foot per second. And it's feet, because I stole this from an American. Should be 1 meter. It's Canadian or anywhere else in the world. Okay, then you just plug everything into the formula. So dA dt is going to be pi times 2. The radius is 4 feet. dr dt is 1 foot per second. If you multiply that out, you will get 8 pi. Feet times feet is feet squared per second. And the units will tell you if you did it, well, they won't tell you if you did it right, but it'll give you a clue. What are the units for area? Something squared, right? Because it's length times width, or pi r squared, or whatever. We have our feet squared, so we know that it's right. And it's feet squared per second because it's how fast the area is changing per unit of time. All right. Is that okay? Okay. Air is being pumped into a spherical balloon at a rate of 4.5 cubic inches per minute. Find the rate of change of the radius when the radius is 2 inches. Okay, so we need to know the formula for volume of a sphere. You already know that? I will give you these formulas. I'm just curious if anybody knows this. It has to be cubed because it's volume. So volume of a sphere is 4/3 pi r cubed. All right. I want to know how fast the radius is changing. What is this number here? That's how fast the volume is changing, right? Because it's cubic inches per minute. So what's the first thing I do to the formula? Sorry? Derive it, right? If you don't know what to do, just derive it. With respect to time, because it's a rate problem. So dv dt. 4/3 and pi are constants. So I just got to derive r cubed. What's the derivative of r cubed? Yeah, 3r squared dr dt. All right, the 3's will cancel. So we can clean this up a bit. 4 pi r squared. All right, there's our formula that relates the change in volume with the change in radius. Then you just plug in everything you know. So this here, 4.5, is my dv dt. They've told us that the radius is 2. And that's it, because they want us to find how fast the radius is changing. So per minute is equal to 4 times pi. R is 2 inches squared. Running out of room. Equals 4, 16 pi. And then just divide off the 16 pi. And it's 16 pi in square inches, which I didn't write. And the units work out as well because cubic inches over square inches leaves you with just inches. And the answer is 0.09 inches per minute. What do you mean? Like this bit? Well, I could flip it down. If you divide by the bottom fraction, the minutes will be down there. That's why they're down there at the end. I just left it there for now. But you could do that. All right, one more. All edges of a cube are expanding at a rate of 3 centimeters per second. How fast is the volume changing when each edge is 10 centimeters? All right, we have a cube. What's the formula for volume of a cube? Let's go that side. Sorry? It's just whatever the side is cubed, right? So S cubed. And it's a cube, so all sides are the same. So that's why I just called them S, not length times width times height. What do I do if I don't know what to do? Derive it with respect to time. So there's my derivative. That is a 3s squared, sorry. Here, I'll clean it up. Because I dropped down the 3. That better? I want to know how fast the volume is changing. They tell me the edges are changing this fast, so that is ds dt. They tell me what the length of each edge is, 10. That goes into s. So it's 900 cubic centimeters per second. All right. So get your formula, derive it with respect to time, plug in your variables, solve for your unknown. That's it for now. Sorry. Because when I'm doing the derivative of this, I drop the 3 down and then take 1 away and then multiply by the inside derivative, which is ds dt. All right. Okay, so this is part 1. Part 1 is basically you get the formula, derive it. Part 2 is where you have to figure out what formula and manipulate it, and then derive it, okay? So part 1, here's your practice questions. Numbers 1, 3, 7, 11, 13, 15, and 17. I will also hand out a sheet that has some practice questions on it. I don't think I'll start part 2 today because I think people are just burnt from the test. So we'll do part 2 tomorrow. I'll finish marking the tests and then you can come have a look at your test as well. Okay? Yes.